And now we'll have Litao from Hong Kong tell us about QuickSub. Take it away.
Yeah, thanks for the introduction. Hi, I'm Litao, and this is joint work with my advisor, Bruno Oliveira, the University of Hong Kong. So this work is called QuickSub, which is an efficient algorithm for subtyping iso-recursive types. So let's start with some background on recursive types. We know that recursive types are useful for defining recursive data structures, like objects. So with this syntax of recursive type, in your type language, you are able to represent formally, for example, a class object that is self-recursive with a recursive record type. And there have been a lot of studies on formalization of recursive types. And there are mainly two flavors, iso-recursive types and equi-recursive types. And our focus today is iso-recursive types. So one important feature of iso-recursive type is that it does not treat recursive types and their unfoldings as equal, but instead you need to insert these explicit term-level unfold and fold constructs to convert between terms that are of recursive types and their unfoldings. But still, you can have subtyping between iso-recursive types if your two recursive types have the same levels of unfolding. Iso-recursive subtyping have a few advantages over equi-recursive types or subtyping. The first is that you don't have to do co-inductive reasoning with the type equality definitions as seen in the equi-recursive types, so it usually gives you a simpler meta-theory. And that also makes it easy to extend iso-recursive subtyping to more advanced type system features like recursive modules or bounded quantification and so on. And another benefit is that with iso-recursive types, you get more efficient meta operations like equivalence checking. But one missing gap that we've noted in our work is that there currently is not a efficient algorithm for subtyping iso-recursive types, and that motivates our work called QuickSub. So before I introduce the technical details of QuickSub, let's first take a look at some examples to get some considerations for what types can be in this iso-recursive subtyping relation. So the property here is kind of expected for iso-recursive subtyping, which is usually called unfolding lemma. That is essential for type safety if you want to have a calculus for iso-recursive types. So it states that if two recursive types are subtypes, then their unfolding should also be in a subtyping relation. So the first observation is that positive subtyping, which means that all the recursive variables appear positively or more intuitively to the right of function arrows. For this kind of types, it is easy to check. You can just compare their type body. So these two types are subtypes. And you can check that by doing one-time unrolling, two-time unrolling. And you will see that all the comparison you get is between this top type and integer type at a contravariant position. So that holds. Negative subtyping, in most cases, has to be rejected, like these two types. And you can check that by, so one-time unrolling is fine. You get int less than top. But if you unroll it two times, you get a contravariant comparison in the which requires that top to be a subtype of int, and that does not hold. So you have to reject this pair of subtyping. But there are also exceptions to negative recursive types. For example, you still expect reflexivity between these negative types. And also, if you have top types in your recursive type, it is sometimes fine for these two types. And you can check that by doing an unrolling, and you will see this negative occurrence of the recursive unfolding is subsumed by this top type here. And the problem of iso-recursive subtyping can get even trickier if you have nested recursive types. So these two types seem to be subtypes if you just look at their body, but actually they are not, and you can check that with the unfolding lemma by unrolling alpha and beta at the same time. So with all these considerations, perhaps the most widely used rules to subtyping iso-recursive types is the Amber rules proposed by Cadelli back in the 1980s. So the Amber rules basically introduce a special context that allows you, when comparing recursive types, you can introduce an assumption that the recursive variable of the first is the subtype of the second into the context, and then you can compare the recursive type body. So with the first two rules, you are able to deal with these positive subtyping cases, as well as ruling out these problematic negative cases. But these two rules cannot account for reflexivity. So in particular for negative subtyping, so in order to get reflexivity in your subtyping relation, you will need this extra amber self rules to allow reflexivity. And that gives you an efficiency concern if you want to implement the amber rules, because you essentially need to do backtracking on these two rules when you compare two recursive types. And that can be costly if you are dealing with nested recursive types. And another efficiency concern is that the amber rules require these recursive variables to be distinct in order for this rule to make sense, which is a non-trivial requirement in practice. And if you're not dealing with recursive types that satisfy this assumption, you will need extra runtime overhead for renaming. So with these inefficiency concerns with the amber rules, our work proposed QuickSub, an efficient algorithm for dealing with iso-recursive subtyping, and we prove it to be equivalent to the amber rules. And for the rest of this talk, I'm going to use this notation, although it is written in a judgment form, but it can be interpreted as an algorithm by treating this context polarity mode, which I will explain shortly, two types as input, and also we change this. We introduce a meta variable that can be ranged between strict subtypes or equivalent result as also part of the judgment, and you can treat that as output. So this notation is no longer part of the subtyping judgment, but rather it's a meta variable of representing subtyping result, and you will treat it as a output of an algorithm, and our algorithm will actually return failure if no rules apply. So as you have probably noticed from the design of these notations, there are actually a few key ideas in QuickSub. The first is that we are tracking polarities by introducing the polarity mode that can be either positive or negative to all the variables in the context, as well as the judgment form itself. So when you compare two recursive types, you will introduce the recursive variable into the context, as well as the current polarity mode. And when you go into the contravariant case, when you compare function types, you will flip the mode of the judgment. And this implies that if you end up with a variable that is you need to retrieve from the context that has the same polarity as the current judgment polarity, then that indicates the current alpha is positive at that point. Otherwise, it's negative. So this gives us an efficient design of tracking all the polarities efficiently in the algorithm. Another idea is that our algorithm now distinguishes strict subtypes from equivalence all over the judgment. So this can be implemented by first precisely tracking these base cases, and then compose them where necessary. For example, in the function case, you only get equivalence from composing two equivalence results. Otherwise, you get strict subtypes. And by treating the positive variables to be considered as equal, we are now able to deal with the positive subtyping examples from our first observation. But as I have said, the trickier case is negative subtyping. So now let's deal with it. The goal is we want to check subtyping by directly comparing the type body. We do not want to introduce extra rules that requires backtracking, renaming, or unfolding. So actually here in the design of QuickSub, we make a more general observation from the example that when negative recursive variables are compared with themselves, they essentially create a constraint that the recursive type they correspond to should be equivalent. So let's consider this invalid example we have seen before. So it fails because at the end of the derivation, you are comparing alpha in a negative position with it itself. And that contradicts with the fact that what you get from the type body is not an equivalence result. So that caused the subtyping to fail. But if this alpha, although appearing in a negative place, but it's not compared to itself, but top type, then it is still fine for the subtyping relation to hold, like for this example. So with this observation, we are able to deal with negative recursive subtyping. And in the implementation, to capture this idea, we introduce what we call equality variable sets, which are annotated to every equivalence result that captures these constraints. So for positive variables, they don't create these constraints. But for negative variables, you will need to add the current variable to the constraint set, so that later, when you can, for example, in the function case, we are now requiring that every time you compose an equivalence result to a strict subtype result, this constraint set, equality constraint set, has to be empty. Otherwise, it will immediately fail the subtyping check. So with this design, we are able to disprove such negative subtyping examples. And also, although you have this equality variable sets, you can still propagate equivalence results from type bodies to a recursive binder, except that you essentially need to do some bit of rewriting of the equality variable set here, but I don't have time to explain that. You can see our paper. Basically, we design a rewriting strategy for this equality variable set so that our algorithm can also handle a nested recursive subtyping in a correct way, in addition to ensuring reflexivity. So that's basically all the ideas in the QuickSub design, and you can see this QuickSub can actually be implemented in a functional style, and you can check all these cases are disjoint from each other, so you do not need to do backtracking. That gives you a linear traversal of the size of the types. But we do have a little bottleneck here, which is the set operation that you need to do in order to ensure correctness, which is on the equality variable sets. But in our implementation, we can optimize them using imperative data structures. So the basic idea is to update it on the fly and when you're doing the subtyping checks. And that will give us a linear cost, which is in terms of the number of total recursive variables in the worst case. But we will show that for practical case, this is often a constant complexity. So overall, QuickSub has a OMN cost in the worst case and linear for practical cases. So in order to check our claims here, we actually performed an evaluation in our paper. So we implement QuickSub in OCaml, and we compare the performance of QuickSub with other existing algorithms, including the Amber rules, as well as nominal unfolding rules, which are recently proposed that have proved to be equivalent to the Amber rules, but addressing meta-theory challenges. And although nominal unfolding rules are algorithmic, but they are not designed with efficiency in mind, as we will see later. And we also compare to the complete iso-recursive subtyping work by Ligati and other authors. And their rules are more expressive than the Amber rules, but in their work, they actually do implement an efficient OMN algorithm. And in the paper, we also compare to equi-recursive subtyping. So we evaluate all the examples, all the algorithms on examples that we come up with to capture the different recursive type patterns you would normally encounter when you are doing programming. For example, in practice, you may write these nested recursive objects, and we use this kind of patterns to do our evaluation. And you can see that as the depth of the recursion goes get large, so for this positive nested recursive subtyping pattern, the Amber rules and the complete algorithm are actually quadratic or even worse in terms of complexity, but our QuickSub remains linear and efficient. And in the paper, we have more patterns to evaluate different patterns benchmarks. And here I just visualize them using a bar chart, and you know that the time scale is logarithmic. And the results show the QuickSub outperforms other algorithms in most cases, except those reflexive cases, because we implement the Amber rules in a way that it always tries reflexivity before backtracking. So in these cases, reflexive cases, the Amber rules will perform faster, which is kind of expected. And overall, the evaluation shows that QuickSub handles both simple and nested recursive types efficiently, and that gives you linear performance in practical scenarios. And one interesting case might be the worst case pattern. And the worst case scenario actually only occurs here when all the variables are negative and the subtyping and the two types in your subtyping relation is equivalence, so that you need to frequently operate on the equality variable sets, and the maximum size of the equality variable set is the number of recursive variables. So that, as we have shown, the complexity is OMN, but since we have this imperative structure of, in our algorithm implementation, this optimization, QuickSub still demonstrates an efficient performance compared to other algorithms like the complete rules. So to conclude, we present QuickSub, an efficient algorithm for Iso-Recursive subtyping with linear complexity in practice. And you can find more in the paper about, we do have a mechanized ROC proof that shows equivalence to other Iso-Recursive subtyping formulations, as well as a type soundness proof for calculus using QuickSub. We also extend our algorithm to support record types to give more evaluation examples, as well as a demonstrator of scalability. In the future, we plan to extend QuickSub to handle more type system features, and also we're trying to deal with equi-recursive subtyping using these ideas. So that's all for my talk. Thank you for your attention.
Okay, questions?
Could you talk more about the extensions that you're thinking of? So for example, if we want to add just union types without any distributivity, would that be a trivial extension, or does adding new features really make sort of calls for extra, I don't know, handling of polarities or something like that?
Yeah. So I think we can decompose your question step by step. So for union type or intersection types, I will expect it to be easy, because although you cannot avoid backtracking when you're doing intersections and unions, but you can still apply this idea to kind of avoid unfolding or backtracking for recursive types. And in terms of distributivity on union types and intersection type, I'm not sure if that's what you meant. The problem itself, I think, is already kind of tricky. And there are actually, I don't think in theory they have a good, so maybe the first step is to think how, before the algorithm, to think about the rules, and so, yeah.
Yeah, no distributivity.
Okay, yeah. Since in our group, we have a work on combining this formulation with bounded quantification using nominal unfolding rules, I briefly mentioned. So we're considering, in that case, how to implement QuickSub with bounded quantification efficiently. Yeah, thanks.
More questions? I feel like I saw a hand, but then it went down. Oh, no. So I have a quickly naive question while the next speaker gets set up. I'm used to a formulation of the Amber rules with only two judgments, which lacks the reflexivity judgment. This is obviously a limitation for expressiveness, but what I'm not quite sure of is what sort of compelling programs will fail to type check under this more restricted Amber set, which will be allowed with the presence of the reflexivity rule, which is also your source of complexity.
You mean that the Amber rules is, sorry, can you repeat the?
Yeah, sorry. Once upon a time, I read Types in Programming Languages, and in that book, the Amber rules are presented with two rules, and they're missing the reflexivity rule. Yeah. That formulation doesn't have any of the computational complexity, but it gives up a little bit on expressiveness. Yeah. I'm wondering if you can comment on, a particular example program or type of example program that we would want to type check, but would fail to type check without the reflexive rule.
I think the reflexivity is kind of expected. Otherwise, you'll get other problems. I'm not sure I'm completely understanding your question, but yeah, maybe we can take that offline.
I did say it was a naive question. Let's thank the speaker one last time.
Thank you.